I remember seeing things like that. You guys
Have your practice problems. Last time you did that. Oh, you got you. Got them.
guys can.
Yeah.
Actually, we'll do that too.
Well, yeah. I know, we were like getting our bus to leave. It's like really bad in my life.
Unfortunate.
Yeah. Thank you. So good.
The other one
And then Maddie and I are making taco soup.
Okay, so the next thing going out is an assignment for Monday.
Like do Monday?
Due Monday. Mhm. So with the links, you can find those right. Of course, make it easier for you to go to the link. So just the assignments folder there, and then you can just click. So what I'm giving you now is just available right there. So again, this is just due on Monday.
Trying to stop you after looking.
Okay, so welcome. So what I'd like to do for today, my goals to finish chapter 5, start chapter 6, and then we have an open note pop quiz right at the end of class today. So we'll do those three things. So how do we define the center of gravity? How would you define the center of gravity of an object or body represents what? I like that word balance point. So it's a point around which the mass of a body is equally concentrated or balanced. So the center of gravity and center of mass for our purposes are the same thing. So use those synonymously, center of gravity or center of mass. And so we had this practice problem where we located the center of gravity of the barbell, which is really dependent on how the mass is distributed. So in this practice problem, we had more of the mass distributed to the right, which means that the center of gravity is no longer exactly in the center. So if both of these plates had the same mass, then the center of gravity would be right in the middle at 1.1 meters. But because one plate has greater mass versus this plate over here, if we define this as our axis, then the center of gravity is going to shift just a little bit. So the center of gravity is going to shift to the right because more mass is concentrated on that side of the barbell. So center of gravity is a very important concept that affects stability. So the position, welcome Levi, the position of the center of gravity affects how well an object or body can be in balance. So the last part of chapter 5, we have just a few more slides to go. We talk about total body stabilizing factors. So factors that determine how well an object or body can maintain balance and equilibrium. We can also use these in a practical way as prescriptive factors for exercise. So we can make an exercise more difficult or less difficult using these 3 different factors that affect stability. Hi, Caitlin. You need some help? Okay. All right. So there's 3 factors, total body stabilizing factors. So the first one is weight. So things that have greater weight are going to be more stable. So an object or body that has more weight is more difficult to knock off balance, we could say. So an object or body that has more weight has a greater tendency to maintain their position. So they have greater inertia. There's more difficulty in changing their position when an object has greater weight. The second one is the height of the center of gravity. So as mass is distributed higher off the ground, there tends to be less stability. So that's an important factor for exercise prescription especially. So how many have compared the amount of weight you can hold on your shoulders and do a back squat with doing an overhead squat? So holding a weight above your head and trying an overhead squat. So as I'm seeing a few head nods there. So obviously the overhead squat is a lot more challenging due to several factors, but one reason is we have less stability because when you lift a weight over your head, what happens to the center of gravity for your, if you consider the weight in your body is a system. Yeah, so the center of gravity would be higher. And so that forces especially our torso muscles around the middle of our body to activate to keep our spine more stable. So we can do all kinds of exercises with the weight positioned overhead. How many have done overhead lunges or different types of things where the weight's overhead is the same concept. So anytime you walk or squat, lifting a weight overhead creates more demand for these muscles that serve as stabilizers of our spine. So the very last factor, the area of the base of support. So this has a lot to do with your stance. So from a practical standpoint, how are you standing when you do an exercise? So how are you standing in the context of different sports skills? So in football, there's probably more positions that are thought to be more stable than other positions, and so you want to maximize your stability if you're going to be, if an opponent is going to be applying force to you, because if you can be more stable, there's less chance that you're going to be knocked off balance. So creating more stability means that we want the center of gravity away from the edge of our base of support. So base of support is basically the area around and between your feet. So it has to do with the number of contact points. So for example, in football, a 3-point position or a 4-point position, in track, a 4-point position, standing on 2 feet, how you position your feet relative to an oncoming force. It's basically drawing a line around the perimeter of your feet and then shading in the middle. So that represents the area of the base of support. So gravity acts on our bodies straight down through the center of mass. So gravity applies a downward vertical force to our body through our center of gravity or center of mass. So the position of our center of mass is really important because gravity acts through that, but how close that point is to the edge of our base of support is really important as well. So there's times in sports where we want less stability. There's times in sports where we want more stability. So it all depends. So if you want less stability, you want to be able to move out of a position quickly. You want the center of gravity to be closer to the edge of your base of support. If you want to be more stable and more difficult to be knocked out of position, you want the center of gravity to be further away from the edge of the base of support. So if I was standing with my feet together and I started to lean this way, if I keep going, what's going to happen? I'm going to tip over because you lose equilibrium and you fall when the center of gravity falls outside your base of support. So as long as my center of gravity is within my base of support, I can maintain my balance. But as soon as that center of gravity falls outside the base of support, I'm going to tip over. So the center of gravity has to be within that base of support to stay in balance. So this is a premium in football. Not sure any of you are football historians. The 1985 Chicago Bears, thought to be one of the greatest NFL teams in history. Anybody read about or know? No? Okay. So William the Refrigerator Perry was kind of ahead of his time in terms of size. He was about 350 pounds. His Super Bowl ring size was the largest of any football player. His ring size was 25, so that's a pretty big ring. But the reason I bring this up is not just because he's awesome, but because there's a lot of weight there, and so he had a lot of stability. If you go back and watch that Super Bowl in January 1986, he actually ran a touchdown in the Super Bowl, so that was really special to see. They played the Patriots that year in the Super Bowl. So how many know this guy, Barry Sanders, who was thought to be arguably the greatest running back of all time, and he retired while he was still kind of in his prime, and so he's still very healthy and functional. But one of the things that made him so great was he's got these big tree trunk legs. So if you're someone that has really big legs, why would you excel at football? You're probably really fast because of that, because you have lots of muscle that can move your body, but what else? What does that do to your center of gravity? Lowers it, which does what? This keeps you stable. It makes you harder to knock off balance. So you combine his quickness with that stability, and that's a good running back. Okay, so let's go back here. So which is more stable, this one or this one, and why? So two different shapes where a force, P is a toppling force. So we're trying to knock over this shape, this object. Which one is more stable and why? Yes, so why would you say that? Has to do with the Yeah, so this is the tipping point down here. And so once this center of gravity falls outside that tipping point, what's gonna happen? It's gonna tip over. So the greater the distance between where the center of gravity acts and we could say this is the axis or the tipping point, the more stable. So we can apply this to sports scenarios where if you can establish a position where your center of gravity is well inside the base of support, or increase the area of the base of support, you're going to be more stable versus over here. Okay, now here's an example of a sport where you want less stability in the start. So you want to be able to get out of that position as quickly as possible. Not too quick though. How many of you have ever seen a situation where they lean just a little bit too far before the gun goes off and there they go into the pool? So you want to be able to get out of that position as quickly as possible. You don't want to be so stable that it slows down your ability to start once you hear that signal. So you're carefully moving your center of gravity as close to the edge of your base of support as you possibly can, still maintaining stability, waiting for that signal so you can quickly start the race. So here's just another sports-related example. Which one would be more stable? Yeah, depending on where the oncoming force, if the force is the opponent's coming from this way, okay, so the larger base of support here would obviously be the more stable position. Okay, so just a few comparisons. So if you're having a hard time with visualizing what base of support means, this gives you an example. So just the perimeter around the contact points and then everything in between. So the area of the base of support. So a 4-point stance has a larger base. And so people will oftentimes use tools like this if they have injuries to increase stability due to the greater base of support. Go in here. So how many of you can do that? Maybe we should do that right now. No. Okay, yeah, very little base of support there. Ballerinas have lots of force on their feet. I have a cousin that was a ballerina, and she actually has some damage to her feet because of all the years of doing this type of stuff. Okay, so just different bases of support. And that's the end of chapter 5. So do you have any questions? Any questions? Okay, so I think we're good to move forward. Chapter 6. So angular kinematics, a few chapters ago, I think it was chapter 2, we talked about linear kinematics. So there were 3 variables from a linear standpoint that we talked about. Do you remember? I'll bet you do. Let me tell you the definition and see if you can pick the right word. So what do we define as a straight line change of position? The D word, right? Displacement. No. So displacement is a straight change of position in a straight line. Okay. And then what's the rate of change in position? So displacement divided by time gives you what? Velocity, yeah, so the rate of change in position. Okay, and then the rate of change in velocity is what? Yeah. Okay, so from a linear standpoint, we have units to express each of these. So International System of Units. From a linear standpoint, it's, I'll just write down below here, meters. And then of course, as as you know, meters per second. And then remember what acceleration is? Yeah, meters per second squared. Like that, okay. So chapter 6, we are changing our perspective to be more angular, so around an axis. So it's not linear movement anymore. Linear movement can be translation along a straight line, or it can be along a curved line. Like that. So that's linear movement. So angular movement is rotation about an axis. So we have clockwise and we have counterclockwise. So we have a central axis around which movement is taking place. So we have angular displacement. So displacement from an angular standpoint. But the units are different. Units are different. So we don't measure objects or bodies that are traveling around in a circle. We don't measure that in meters. So we use units that are different. So probably one that you're most familiar with, like in kinesiology or foundations lab. Do you remember the tool, the goniometer, that you measure range of motion? So what are the units on the goniometer that you measure hip flexion or shoulder actions? Yeah, degrees is right. So you have displacement or change of angular position is expressed in degrees. Okay. Another one that you may have heard, revolutions. Okay, so how many degrees are there in one revolution? Yeah, 360 degrees per revolution. So you can transfer between angular units. So another one that bring back your high school geometry nightmares, maybe, radians. Do you remember that one? Yeah, radians. So there's different ways we can express angular displacement and convert between those units. So, for example, there are 57.3 degrees in 1 radian. So the rate of change in angular position would be defined as angular velocity. So how fast an object or body is rotating about a central axis. So you could take any of these units and you could say, okay, you could say degrees per second would be one way of expressing angular velocity. Radians per second, revolutions per second. What about this one you may have seen in your car? RPMs, what does that stand for? Yeah, revolutions per minute is just another way of expressing angular velocity. So revolutions per minute, that's angular displacement in a unit of time. So logically, the rate of change in angular velocity would be what? Not linear, but angular. Acceleration. So the rate of change in velocity would give you seconds squared. So one way of expressing this would be degrees per second squared or radians per second squared and so on. So it's just looking at movement, circular movement rather than linear movement is the idea. So are there any questions on that? Usually with movement we call it general motion, where we have components that are linear and components that are angular. So we usually analyze the linear part separately from the angular part. So we put them both together, like a cyclist that's traveling down the street. If you look at the whole thing, it's linear, but if the action of the feet pedaling the bicycle would be an angular part. So normally most movements have both in some way. All right, so angular movement, rotary movement about a central axis. So that's how our bodies move, right? Remember from kinesiology, planes and axes? So the three planes, sagittal, frontal, transverse. So you move through a plane about an axis. So an axis has a 90-degree relationship to the plane of motion. So movement through the sagittal plane would revolve around the frontal axis, right? Movement about the frontal plane would revolve around the sagittal axis. Movement around or movement in the transverse plane would revolve around the longitudinal or vertical axis. So the movements that we have in the body, the joint actions, flexion, extension, abduction, adduction, these are circular, angular type movements. And so we describe those movements in the context of the plane and then around an imaginary axis that goes through the joint. So angular position is expressed with the angle theta. So the intersection of two lines would be described as an angle, and we use theta to define that angle. So our units for angular position can be in degrees, radians, revolutions, as we said. So we can transition between units. So 57.3 degrees in 1 radian. Remember the end of chapter 4, the geometry of a circle. So 1 revolution, or 360 degrees, the circumference of a circle, so all the way around, is equal to 2 pi r. So we're coming back to this just a little bit. And then 1 radian is equal to 180 degrees divided by pi. So angular displacement is defined as a change in angular position. So you have the final angle minus the initial angle. So that gives you the change if you look at the final angular position versus the initial angular position. So that brings us to what we ran into with linear motion and the difference between displacement and distance. So from a linear standpoint, how did we define the difference between displacement and distance? So displacement was a straight line. How was distance different? Yeah, Eric. So that it's the total length of the path traveled by an object or body. Whereas displacement is just straight line start to finish. So if your finish point is the same as your starting point, your displacement is 0, but your distance is different because it looks at how far in total. So angular displacement and angular distance are the same concept. We're just talking about angular movement. So take shoulder abduction, for example. So if I did this with my arm, if I abducted and then I adducted, what's my angular displacement? So I started here, and I ended here. What's angular displacement? It'd be 0 degrees, because my start and finish were at the same point. But if I look at angular distance, if I did this and this, how far did I go roughly from a distance standpoint? Yeah, 360, because from here to here is how far? 180, and then back would be another 180. So the angular distance would be 360 degrees. So in cases where angular displacement and distance are the same, if I'm just going from here to here, what would my displacement be? 90 degrees. What would my distance be? 90 degrees. So as soon as you have a change in direction, then displacement and distance are going to be different. So here's your first formula for the chapter. So very important to be familiar with this very first formula. So a simple example of elbow flexion. So our axis is the elbow joint, and then we have 2 points, one on the forearm and one out here on the wrist closer to the hand. And so this little L-shaped, I'm not sure, that must be Greek, but I'm not sure which one, but that represents the arc length. So that's the linear distance that each point travels between the initial position and the ending position. So which point, A or B, has the greater arc length or linear distance? So yeah, A. Yeah, that's right. So A has this right here, so it has this big arc to get to this position, and B right here has a smaller arc. Okay. So the arc length, or the linear distance traveled by each point, is proportional to the radius. So the radius represents this distance between the axis and the point. So from here to here would be the radius for point B, and from the axis out to out here would be the radius for point A. So can you see how the arc length and the radius are proportional? So as the radius goes up or increases, the arc length also increases. Okay, now let me ask you, this is a crucial question to understand. Theta, that represents the angular displacement. So for points A and B, the angular displacement was exactly the same. So from an angular standpoint, both points had the same starting position and the same ending position from an angular standpoint. So we're going from the elbow is almost fully extended to where the elbow is mostly flexed. Okay, so say from 140 degrees to wherever we end off right here. So the angular displacement of both points is exactly the same. Both points went the same amount of degrees from the initial to the ending position here. The difference was in the linear movement. So the arc length traveled by point A versus point B is different. And that's proportional here to the radius. So the distance of a given point from the axis of rotation. So what does this have to do with sports? So let's tie all this back into the practical stuff. So the equation for linear speed, you know what that equation is, we went over it. So linear speed is equal to linear distance divided by time. So let me ask you a question. how did the time compare for point B versus point A? Point A to go from here to here, and from point B to go from here to here. How did that time compare between those points? Was it the same or different? It'd be the same, exactly the same. So this point is going from here to here in the same time as this point is going from here to here. So the same angular displacement, the same time, but what's different? Point A, which one had greater linear distance? Point A. Point A had this great big arc. So it traveled this arc in the same time period as B traveled that arc. So if we consider that linear speed is equal to distance divided by time, if A traveled a greater distance in the same time period, which point is going to have a greater linear velocity? Point A is going to have a greater linear velocity, because it's traveling a greater distance, linear distance over the same time period. So how does this apply? So what is the application? So one advantage of muscle insertions closer to joints is that the velocity is magnified at the end of a limb. So muscles have a very limited ability to shorten. Muscles can generally only shorten it to about 50% of their resting length. So a relatively slow contraction velocity in a muscle is going to be amplified at the end of the limb or implement that's being held in the hand. So take this example. So the insertion of the biceps on the forearm, if its insertion is only 1 inch from the elbow joint, so that's your axis, and the hand is 10 inches from the elbow joint, when the arm rotates, we're talking about linear velocity here. The linear velocity of the hand will be 10 times as fast as the velocity of bicep contraction. Okay, so if they're undergoing the same angular displacement in the same time, the point further from the axis will travel a greater linear distance in that given time period, which means a faster linear velocity. So you can see a pitcher with really long arms has what advantage? The contraction of that pitcher's muscles is going to be amplified all the way out at the end of the limb where they release the ball. And generally, if you look at a lot of pitchers, how are they built? They're really tall and they have really long arms. And so that provides an advantage in terms of release velocity. So the insertion of muscles close to joints allows a relatively slow, we're saying we're giving maximal exertion, but in relative terms, it's a slow muscle contraction to be amplified at the end of a limb or implement. So that's where you're making contact with a ball, or releasing a ball, or kicking a ball, or delivering a punch, okay? The slower contraction velocity of the muscles is amplified the further that point is from the joint axis. Okay, so other sports applications. So several sports. You watch the Olympics with diving and gymnastics and figure skating. The total number of spins is a measure of angular distance, so revolutions. So there's a connection between angular motion and linear motion. So as a pitcher goes through a windup, they're generating angular momentum all through the kinetic chain. So they push into the ground applies that reactive force through their feet, and so during the course of a windup, we're building this angular momentum across multiple joints. So as more of this angular momentum builds, that culminates in the velocity of release. So is it always the strongest person that can throw a ball the fastest? No, it's not. It's the person that can effectively use their body, the kinetic chain, if you will, to build angular momentum so that it's maximized at the point of release with the ball or contact with the ball. So this is your first over the weekend. If you look on your assignment, this is the very first one. So you'll click on the link that's given there, and then you'll watch the application here for golf. So here's your first practice problem for the day. So you've got a sheet of paper. So remember we talked about all of the points having the same angular displacement. So if we can set the angular displacement of the hands equal to the angular displacement of the putter head, and then if we know that we can rearrange that equation to where the angular displacement is equal to the linear distance or the arc length divided by the radius, then we can solve for the arc length of the putter head. So let's get a new screen here. Okay, so how many of you got the PowerPoint up to where you can see? Okay, so for the hands, arc length of the hands divided by the radius for the hands is equal to the arc length of the club divided by the radius of the club. Okay, so let's put in some numbers. So what's the arc length of the hand? What does it say? Let's read through the problem there. Yeah, so it's 10. And how far are the hands away from the axis, which is back? End of the, 50 centimeters. So what's the arc length of the club is actually what we're solving for. So that's what we want to know. What's the radius of the club? So how far is the head of the putter from the opposite end of the club? 150. Okay. So how would you go about solving that problem? What could you do to solve for the arc length of the y'all know just your algebra, right? So you'd multiply both sides of the equation by what? 150. Cancels on that side. So the arc length of the club is, and that's because of the radius. So the difference in radius is, the radius is 3 times that of the hands. And so you'd expect the arc length to be 3 times that of the hands as well. So the arc length of the hands is 10, so the radius is increased by a factor of 3, so you'd expect it to be 3 times as well. So okay, so some other practical examples here. So chapter 5, we talked about different activation strategies for the squat. So this would be a low bar back squat, this would be a high bar back squat, this would be a front squat. And so we've got angles at the hips, at the knees, and at the ankles, as well as the back relative to the ground. So these angles are important because they define the technique of each type of lift. So you can see that the back angle is a little steeper in this case. So the hip angle relative to a front squat, you can see the hip angle is pretty large here between the torso and the femur. So this angle is large. And then as the bar goes around the back, this is a high bar back squat, so the hip angle is a little bit smaller. And then the low bar back squat, you have this nice, you're leaning forward just a little bit more, so there's an even smaller angle between the femurs and the torso there. The knee angle too. So in this case, you can see the front squat, you're sitting back just a little bit more, so the knee angle is a little smaller between the femur and the lower leg. And then the knee angle gets just a little bit bigger as you go back here to the low bar back squat. So this has a lot to do with technique as well, because with good squat technique, we want the hips and shoulders to rise at the same pace. So everything coming up together. In this case, though, this would be bad squat technique because the hips are coming up faster than the shoulders. So this would probably indicate a lack of core strength to keep the pelvis or the torso in the right position here. So the hips are coming up faster than the shoulders in that case. So you can see, you can look at moment arms here with each of these lines relative to the knee and the hip joint. Okay, so this is an example of 2 world record performances for the snatch. So how many know what a snatch is? So that's, you go from the ground to over your head in one quick motion, and then you have to be quick enough to get underneath the weight and then catch it. So it's one of probably the most skilled type of lift that you can learn to do well. Takes lots of practice to be quick enough to get under that weight and then to be able to catch and stabilize it and then to stand up with it. It's pretty amazing. So at the time, this data was, I'm sure the world records are different now, but at the time in 1986, these were both world record performances at their respective weight classes. So you have 2 people of different heights, and you have angles all the way through from the start to the completion of the lift. And so this line here just kind of follows the path of the bar for each lifter. So what I want you to do is look at the difference in the knee and the hip angles at position 5. So both of these lifters, great lifts, great techniques, but because they have different proportions, the angles are going to be just a little bit different. So if you look at position 5 here, and you look at position 5 here, okay, look at this lifter in particular, their hips are back just a little bit more, whereas at 0.5 in this case, the hips are starting to open up a little bit more just before they start to initiate, just before they start to drop into the catch. And so you can take a look at these angles and you could probably deduce that at this second pull right here, this lifter is probably going to be a little more quadricep dominant because you see they're kind of sitting back just a little bit more. There's a little more flexion in the hips. Whereas this lifter right here, if you look at that, their hips are starting to open up more. They're probably a little bit taller And so they have to extend their hips earlier so that the bar is going to clear their knees. How many of you have ever come up out of a clean and just scraped your shins? Okay, so this lifter, because of their height, they have to extend their hips a little bit sooner so they're able to get the bar past their knees. So a taller lifter is going to have a little more hip extension dominant type strategy to effectively get the energy into the bar before they start to drop underneath it. But this is just to emphasize that both outstanding performances, but there's differences, subtle differences based on body proportions like height. Okay. So this is the second part of your assignment for the weekend. If you look here, some stuff about Usain Bolt and speed. So speed is equal to stride length multiplied by stride rate. So I've got these mixed up. This should be meters per stride, should be stride length, whereas stride rate should be strides per second. So I'll fix that in the PowerPoint, but should be the other way around. Meters per stride is stride length, strides per second is stride rate. So as a sprinter, you work on both of these components. So you work on moving your legs faster, which is strides per second. So there's high-speed treadmills and assisted. How many have done assisted sprinting, where you're actually being pulled by another sprinter in front of you? So you're attached to another sprinter who's pulling you. That's a way you can improve stride rate. So you're teaching your nervous system to turn over your legs faster with those high-speed techniques. And then stride length, that's just practicing regular explosive type strength training, because the more force you put into the ground means what for your stride length? If you put more force into the ground, you're going to travel farther with each stride. So the ground reaction force is going to push your body down the track further. So there's different techniques that sprinters use to maximize both those parts. But stride length is really, really important in terms of the distance that you cover with each stride. So that can be important for distance running. If you look at maybe a recreational runner and their stride angle here is 90 degrees. A guy like Usain Bolt, the stride angle here is 112 degrees as he's pushing there. And then this guy right here, Wanjiru, who has set world records. He still holds the Olympic record in the marathon at 2 hours and 6 minutes. He tragically passed away a few years ago. I'm not sure what the story, I don't think they ever released the story, but he fell off a balcony and tragically died at a young age. But he did set some world records here, and you can see his stride angle is a lot wider here. So you're just covering more ground with each stride, which makes you more efficient and faster. So how could you improve your stride angle, do you think? Yeah. What else could you do? Mobility is right. Mobility. It takes patience. That's the one component we think. We think conditioning and we think weights, but do we think enough about mobility? That's an often neglected part of the whole training plan, is the mobility part. So by improving hip mobility, we can improve our stride length, and that, based on our speed formula, is going to make us faster. So that's chapter 6, part A. Do you have any questions? Okay, so this pop quiz is going to be open note, but not open neighbor. You do need a calculator, and I brought a couple of extras. Is there anyone that needs a calculator? So, yeah, hand up. Okay. Use your comes from last time. You can do your work right on the back of the sheet, or you can do your work on the sheet that we did our only practice problem for today, your choice. Happy St. Patrick's Day, everybody. Oh, it's hard to get over your paper cut. Yeah, sure. Alan, I got a calculator, thanks to Eric.